The monks are over here chanting. From what I can tell, it's right angles. They keep saying something about right angles. So Gram-Schmidt process. Okay, so there's a response there, and they are smiling somewhat weirdly, but I think benevolently. So all right, so that's the path we're going to take. We're going to talk about right angleness. So there are 5 little pieces here. It's all to do with, taking a basis and transforming it into an orthogonal basis. So we're going to understand what this means. We really like right angles. There's nothing being shared between 2 vectors that are at right angles, right? This is this direction. There's no overlap. So they're powerful things. And indeed, that's how everything is built in our basic setup, right? IJK hat. Those too many hats for 3 dimensions, for example. And we do the same thing with Fourier transforms and all sorts of other worlds. All right, so I've written a lot of this out, and that's just the way I'm going to approach this one. So the idea is orthogonal and orthonormal. So that's just a small piece we get to in the second thing here. So I'm going to color this in because it's great. So it's true. It's true. You will make friends if you come bearing orthogonal bases. So there'll be a little bit of motivation for this, right? Given you some already, I suppose. And then we'll also talk about orthogonal matrices. That will come a little bit later on. So there are bases that we make orthogonal, and then we'll have this whole world of matrices. Big deal later on is that all of this stuff will come for free in a very special case, and that's this AX equals B business. We're going to come back to it because that's what this course is about, and it's very important. And the next piece coming after this one will be about the Gram-Schmidt process, which is a way of a method for creating orthogonal bases. All right, so what does this mean? This orthogonal business for bases. So, all right, so the story is we've been finding bases for our 4 fundamental subspaces, right? That's the way this course has worked. We found subspaces, and then we got to this next idea, which was, well, let's find a basis for it. And we end up with quite a beautiful story, right? With the reduced row echelon form of A and the reduced row echelon form of A transpose. And they gave us bases for these 4 subspaces, but we took whatever we got, right? So there were 3 ways to find a basis for column space and 1 for null space. Row space and left null space have the same story. And we kind of ended up with a best version for column space. All right, words. So, but what if we get a basis out, right? So we get a basis out, and that describes, let's say we're in 3 dimensions. These 2 vectors here, they describe some plane. That's all very nice, but we could have these vectors, and that would be, better in some ways, and maybe we want to rotate it and do other things. But sometimes, so there are an infinite number of bases, in general for non-trivial subspaces and vector spaces. So we want to find one. Sometimes we'll be able to find one. Sometimes it will naturally appear through the magic of matrixology, a really good basis, kind of the best basis. All right. Okay, so remember Fezzik. So Fezzik was a very large matrix in the context of the matrices we play with here, 3 by 4, right? No exercising. And we ended up with a basis for the column space of Fezzik here, right? Column space. If you go back and look, you'll see that we end up with these 2 characters, 1, 0, 2, 0, 1, 1. Now, that's okay, right? Fine. But let's take a look at these. These aren't at right angles, right? So our basic test for right angleness is, and so that's what's being said, right? This is fine, it does the job, but we really like orthogonality. So let's check this. Good, it's fun. So the dot product here, right? So it's 1 times 0, yep, plus 0 times 1, plus 2 times 1, right? So that's 2. That's not equal to 0. So that is, so they're not right? So these are not orthogonal. Sad face. So let's think about, all right, that's just an example. There's something not ideal about it. So let's just move on to some other examples here. So here's a basis for some plane in R3, right? Two three-dimensional vectors. 1, 1, 2, right? 1, 1, 2 and minus 2, 0, 1. We'll call them A1 and A2. We'll try to keep that same kind of structure. Excuse me. And it's a plane, right? So they're clearly linearly independent, so they're not pointing in the same direction. All linear combinations make a plane. And if we take the dot product here, then we'll get, so there's a 1, minus 2, right? So there's a minus 2, plus 0, 1 times 0, plus 2. So it equals 0. Yes. So this is an orthogonal basis. Right, we call such a basis orthogonal. It's an important thing. And here they are, right? So these two vectors are at right angles to each other. And you don't have to know exactly how they point and so on, but they make a plane in, when we take all linear combinations, we get a plane in 3 dimensions. So that's kind of a nice basis. All right, so let's look at another one, just like Fezzik, that isn't great, but it has a better connection. Okay, so it's the same first vector, right? We had this 1, 1, 0, 2. Sorry. Right? 1, 1, 2 there. So that's here again. Okay, so we've got the same initial vector, and then we've got some different vector here, 1, 3, 7. So take the dot product. We've got 1, right? 1 times 3 and 2 times 7. So 1 plus 3 plus 14 equals 18. Famously not equal to 0. Okay. Interesting, right? So, it's all right. But so this is a setup, of course, a contrivance. Let's look at what was done here, right? So this vector A2, I should, you know what, I'm going to connect it here. That's right. So this should be this one. So the sneakiness is that, all right, A2 is minus 2, 0, 1 plus 3, 1, 1, 2. So what's going on here? So minus 2, 0, 1 is back here, right? So it's the same vector we had before, which we know was orthogonal. And then this 1, 1, 2 is the first vector. So the statement is, or the observation is, that A2 contains some of A1. This is a completely manufactured story. So if we could remove this, then we get to A2 is minus 2, 0, 1, and that would be at right angles to A1. Right? So we need some way to chop off this piece that's pointing in the same direction as A1. So maybe, hopefully this will help, right? So if we could break this, right? We want to remove this piece. Remove this piece. And then this would be our new A2 prime. And those two things would be at right angles to each other. So it's projections. It's projections. It's good. We're lazy. We like to use, we're not lazy, but we do like to reuse things because knowledge and power and so on. So this is the big idea. Someone hands you a basis. They say, okay, there's a basis, and you think, it's not so great. You can work through it, right, systematically. We'll turn a basis into an orthogonal basis by removing all the little non-orthogonal pieces. So we take the first two vectors, clean out the second one so that it's at right angles. We go to the third, clean out anything that it has pointing in the directions of A1 and A2. Then it becomes at right angles, and we keep doing that, but our brain has exploded because we're in 4 dimensions. So this is, all right, that's a big idea. Yep. Good. And everything is connected, so this is good. projections will do the work for us? Yes. Good. We know how to do those things. Okay. Rampant craziness. We're going to claim that that orthogonality makes a basis a happy basis. This is a mathematical term, a happy basis, right? So orthogonality makes a basis a happy basis. Right. The pretty clear reason to start with is that the representation of other vectors by this basis is very clean, right? There's no, it should be an ij hat, I hat, j hat, k hat is sort of a good example, is the primary example to think of, or I hat, j hat in 2 dimensions, right? So it's very easy to see how any other vector is made out of those 2 vectors or 3 vectors, right? They're at right angles to each other. So that's the first statement. And so this is this point here, right? Information contained in each basis vector is distinct, right? They have their own special things. There's no overlap. And I've mentioned this. This is a great thing. Later we'll get this, so we'll get to see that orthogonal bases pop out for free for very special matrices. Of course, we're talking about square symmetric matrices, and then we're also talking about arbitrary matrices because we like A transpose A, right? Okay. With real coefficients, real entries. I know. This is a little extra thing. Just quickly go through this. It's a little, so it should be clear that just intuitively, right? So if all these vectors are in a basis, in an orthogonal basis, if they're at right angles to each other, then they're linearly independent, right? So there's no way one of these vectors can be made out of the others. But here's a little proof that just has some nice features to it, and we'll see some other things, right? So it's obvious, but the proof is nutritious, and this is a dangerous word, obvious. I railed against this word many years ago. When I was young, I got sick of the "it is obvious" statement, or "it is trivial," but especially "it's obvious," right? It's always easy to understand things once it's all been explained and so on, so, but it can be hard beforehand. So you should basically very rarely use this word. Yeah, I was in Canberra. That was a long time ago. All right, so this is this statement here, right? So we've got a set of orthogonal vectors is linearly independent. Okay, so let's just go through the mechanics of how we prove that. So we've got a set of vectors, n of them. They're m-dimensional. That's this piece here. Right, so they're still fitting into our m by n framework. We've got, and I need to just clean this up. So this should say, this is the right angle statement, the orthogonality statement, right? For all, right? So the inner products are 0. Dot products, inner products are 0 for all of them, providing I and j are different. Okay, so this is still making this m by n matrix. Good. So we're given this, and we want to show that we have a linearly independent set. So what does that mean? Well, let's prove it by contradiction. So we can presume we have linear dependence, which is to say that a times x equals 0 has a non-zero solution, x, which is to say the null space is not equal to 0. So that's what these things are. Right? So there's some way of multiplying the first column, the second column, third column by some numbers, many of which could be 0, it doesn't matter, and then adding them up to get 0, which in turn means one of them can be expressed as some combination of the others. Okay, so if a times x equals 0, then we can do this. This is a very nice thing, right? So we'll say, right, 0, this is the 0 vector dotted with itself. These are m by n matrices, m by 1, 1 by m. Of course, it's just a 0. So that has to be 0, and we're presuming this is we have an x that lives in null space that's not 0. So we can, right, we're just using the null space equation here. We'll do this quickly, right? So it's blob transpose blob. We know that BC transpose equals C transpose P transpose. Beautiful thing. We're going to use that. All right, use this. So this piece goes to here, the X, and it gets a transpose. A goes to here and gets a transpose. So now we have A transpose A in the middle. We've seen this little beast quite a bit. And we're writing things out. So this is X here, and this is X transpose, I should say, and this is X. So let's look at A transpose A. It's a bunch of times, right? So this is just going to be the columns of A become rows. So it's A1 transpose. Here are the columns. And now just think of matrix multiplication, right? So it's all these inner products. So if you take A1 and then dot it with itself, that's okay. That's going to have, it's the length squared. But dotted with any of these others is 0, right? And that's going to work out here. I'll leave all those things. So we'll end up with A1, the length of that squared, and I'll put an A2 here. Yep, A2, length of that squared, dot, 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 down to AN squared. And then the rest of this is zeros, all zeros. And then this is a diagonal matrix, very important kind of matrix. Very, very lovely matrix. Okay. Which incredibly, every square symmetric matrix is basically a diagonal matrix. We'll get to it. It's incredible. More later. And if you think about how this works, as you multiply these, this is a special kind of structure, X transpose matrix times X. All that gets picked up as you go through, okay, we're good, is X1, whoops, X1 times this piece times X1. And then it'll be X2 times the length of A2 squared times X2 again. So that's this structure popping up. All right, so the last thing to see here is this is equal to 0, right? Dot, dot, dot. Still equal to 0. So this is not equal to 0, right? These are vectors. These are their length squared. And then we've got all these other pieces. So the only way, which equals 0, only if x1 equals x2 equals dot, dot, dot equals xn equals 0. So again, this is kind of an obvious proof. So this is a contradiction. I mean, it's a proof of a seemingly obvious piece, but it's nice to do the math. A contradiction. The null space of A is equal to 0. Which means they're linearly independent. Okay, good. So last piece. So an even better kind of basis in some ways, the orthonormal basis. Right? And it's just simply an orthogonal basis where we've turned all the vectors into unit vectors. Right? The ortho is still there. We lose the gon, which is the angle part, and normalized means. Right. So it's a bit, it doesn't quite have enough words in it. But that's okay. All right, so let's just say, so the observation is this is easy to do. Right, this is easy to do. And so once we have, so what do we have? We have 1, 1, 2. Let me get the right thing. Yeah. So let's say we have 1, 1, 2. And this is the basis we had before, and minus 2, 0, 1. Good. So this is orthogonal. And then we just divide by lengths, right? So this isn't really a matrix operation. We're just going to simply do it. Divide by length. So Boom. So the length of this one, it's 1 squared plus 1 squared plus 2 squared. Yeah. 1 over root 6, 1, 1, 2. And then we have, there's a 4 and a 1, so we've got 1 over the square root of 5. Minus 2, 0, 1. So this is an orthogonal basis. Right, the lengths of those things are not 1, and this is an orthonormal basis. So the hard part, right, so that's what this last piece here is, how to create, how do we do this in the first place? So once we've got an orthogonal basis, this is easy, right? So this should be easy. So this is the hard part down here. Or okay. So that's the next section. This just fell apart on me. Right, so the next section we're going to go through the Gram-Schmidt process, obviously not named with any intent to help us understand what it does. That's okay. And then we'll talk about orthogonal matrices at some point. Yeah, okay. But then very soon we get into eigenvalues, and that is a beautiful, beautiful part. All right.